A very good morning, doctors. My name is Loriza, and I'm going to do a presentation about the basic OP operational amplifier circuit design, one-stage implementation. Okay, my name is Loriza, and my teammates are Haqim and Haziq, Dzul, Afif. Okay, so first of all, I'm going to talk about the content. We include the operational amplifier fundamentals, one-stage design analysis, and also the circuit implementation process. Okay, and for the first step would be the differential input stage. The first section is to accept that two input signals and amplify the difference using rejecting common mode signals. And then next thing is the gain stage. As you can see, the output output voltage is proportional to 1 plus RF over R1 multiplied by the V input. So that's for the non-inverting amplifier. And then for the output buffer stage, the final stage is designed to provide low output impedance and sufficient current drive capability without affecting the amplifier's voltage gain. And first of all, ideal characteristics would be first an infinite input impedance. An ideal OPM draws no current from input sources, allowing connection to high impedance sources without loading effects. That's number one. Number two would be zero output impedance. Ideal OPMs deliver output voltage regardless of load, maintaining constant voltage even when driving heavy loads. That's ideally. Infinite gain, that's also an ideal situation. And lastly is the infinite bandwidth, and OPM that can amplify signals at all frequencies equally, maintaining this high gain consistency from DC to extremely high currents, high frequencies. So for the common applications, this include signal amplification, voltage comparators, active filters, and also instrumentation. You can read it if you want. And then first of all, for the one-stage design analysis, you can see we used two PMOS transistors and also two NMOS transistors for a mirror design. Yes. There's the Vout, the Vin, and the Vin2, the Vin1, Vin2, and there's a capacitor to stabilize the AC current. Not just for the AC current, but also to remove the DC current out of the equation. So the basic differential pair structure uses two transistors with a common emitter or source configuration to amplify the difference between the two input signals. And then for the common mode rejection, rejects signals common to both inputs while amplifying their difference, measured by the common mode rejection ratio. So basically the noise, because usually both of them have noise, so they cancel each other out. And for the current mirror load, it provides active loading for differential pairs, improving gain while maintaining balanced operation across the circuit. And lastly is the input impedance consideration. High input impedance is important for the minimal signal loading, achieved through careful biasing and transistor selection in the differential stage. And for the current biasing principles, first, current mirror copy reference current to output branches using matched transistors, providing stable biasing for operational amplifiers. And for the circuit configuration, two differential transistors share connect gates with reference current in one branch replicated in output branch through match characteristics. And for the temperature compensations, that's not really important because this is simulation. And for there should be also multiple output capabilities. So a single reference current can bias multiple circuit stages through additional matched transistors, ensuring consistent current throughout the amplifier. So for the gain and bandwidth considerations, the gain in OPMs depend on the feedback resistor ratios. For inverting amplifiers, gain is equal to negative RF over Rin, while the non-inverting configurations yield 1 plus RF over Rin, which is the one we're using, the non-inverting configuration. And for the bandwidth limitation, they exhibit gain bandwidth product constraints. Higher gain settings reduce available bandwidth, creating design trade-offs for signal processing applications. And for the frequency response analysis, both plots visualize the OPM performance across the frequency. phase margins considerations prevent oscillation while ensuring stability at target operating frequencies. So as you can see, this one is the first simulation using a DC current. As you can see, for the V1 and the V2, this is the limit for how much it's from in ranges from 10 volts to negative 10 volts. The initial current, current to be amplified, voltage to be amplified is 1 volt, and this is 1000 K, 1000 ohm, and then 9000 ohm. So if you use the from the previous, you can see here 1 plus RF over Rin. The RF is 9 over Rin is 1, so it's 9. So it's 1 plus 9, which equals a 10 volt gain. As you can see, this was the input voltage, this is the output voltage 10 volts, and input is 1 volt. And you can see the same is applied for the AC current. The first, as you can see, this one, it's a non-inverting, right? So this one is the input. You can see it starts at 1 volt and it oscillates oscillates at 5, I think it's 5 hertz. 5 hertz, so 5 times per second. And as you can see, for the output, this is the input and this is the output, 10 volts, and then here is the input. So thank you. That's all for our assignment. Thank you.